So if we zoom in on this lower state, we'll notice that there's actually very close to it, around 2.87 gigahertz with a photon, slightly higher. There is another layer. We call this one the triplet state. We call it triplet state because there are 3 different states, but for our purposes, we're going to ignore one of them. So the 2 layers that we care about, one of them are when both electrons are pointing up, and the other one's when both electrons are pointing down. This is different than our original state down here, where the 2 electrons are pointing in opposite directions. So what happens is that electrons, being tiny bar magnets, like to point away from the external magnetic field, kind of line up with it. And what that means is that if you want them to point into the direction of the magnetic field, you have to apply more energy. And since this is, the energy map is what we're looking at here, what that means is that as you apply more magnetic field, the different spacing between the 2 sets of layers gets further and further apart. And so we call this Zeeman splitting. So how do we take advantage of this phenomenon? Well, so in this excited level, that's about 2.87 gigahertz higher photon-wise. The short of it is that we don't see as much photoluminescence at that level. So in other words, if we have like a little microwave antenna and we're sending in this signal, the electrons are going here, and then we see less light coming out. But let's say we also applied a magnetic field. Then what that does, as we talked about earlier, that splits the levels. And so this 2.87 gigahertz signal doesn't do anything anymore because the level that used to be there isn't there anymore, and so our brightness goes back up. Now let's plot what happens as we scan how much microwave frequency we send in. So basically right here, we're going to have on the x-axis, we'll have the frequency, and on the y-axis, we'll have the photoluminescence. And so if we send in just a little bit of frequency, we see that there's no level right here, so our photoluminescence stays the same. Then eventually we hit that first layer, and so our photoluminescence drops, and then we leave that first layer, and then we keep going, and then, as you remember, there's nothing at the 2.87 anymore, so nothing, 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 nothing. And then eventually we get to the other side, and we see that at a certain point we hit that upper layer, and our photoluminescence drops suddenly again. And so by measuring this gap right here in between the frequencies, in between these drops, we basically can use some physics and math to convert this gap right here to the amount of magnetic field on our sample. And so we can use these sensors as very accurate magnetometers.
This experiment will be set up exactly like our last one. The only difference is going to be that we're going to apply a steady magnetic field and also apply a range of microwave frequencies to the diamond. The purpose of this is going to be to observe the change in the brightness of the photoluminescence as we sweep through a range of microwave frequencies. For this experiment, we're going to turn on our microwave generator and then set the magnetic field to 300 milliamps. Initially, we're going to set our microwave frequency to 2.8705 gigahertz.
All right, so this is the plot we get when we do a few experiments of magnetometry. There are a lot of interesting things to see here. The first one, the obvious one, well, at least to me, is you can see that as you increase the current, which means increasing the magnetic field, the peaks move outwards. So you can see that the blue one is the low one, and then yellow, and it's going in that direction, which makes sense. As we talked earlier, the distance between the peaks should increase. The weird thing is these 2 extra peaks in the middle. What you're seeing here are, so the NV centers tend to have a preferred direction because if you remember the shape of carbon in, carbon bonds inside a diamond, they have this tetrahedral shape. I'm kind of drawing the last one kind of weird way, but and so what you're seeing here is these outside voltages come from the main direction that we're interrogating, And then these inner ones come from the ones that are off at, I think, 120 degrees. And so because there's an angle to the magnetic field that we're applying, in this direction, we don't see a full effect of, basically, they don't see the full magnetic field. They're at an angle to it.